All right, we're back recording. We're in the last few minutes of class. I want to go over with you guys the solution to these first three questions with this turntable. So a lot of students miss these. Right. So turntable, which is spinning, has this radius and this initial angular velocity, so many radians per second it's rotating. Slows to a stop. Stop in 3 seconds. How far did it turn in that interval? Now that is a rotational kinematic question right there. So I'm thinking this right here, right? Oh, zoom out where you guys can see this. Right. Something like this, right? You guys see that? Let me show you guys two different ways to solve this. Right? I think the fast way to solve this question is actually with a graph. It's actually with the graph, right? If you do omega, that's angular velocity in radians per second, versus time in seconds. This thing's slowing to a stop, right? So guys, slow to a stop. What does that graph look like? Here's omega initial, right? So at time 0, it's rotating for, slow to a stop. Does that mean it has 0 final angular velocity, right? And if it stops uniformly, which is a common assumption for this class, right? Can you guys think what that graph looks like before I draw it? Are you guys thinking, that right there? That right there? That's right. That's what you were thinking. Yeah, yeah. And guys, what property of that graph? This graph can tell you a bunch of things, right? What property of this graph tells you how far it's rotated? The area of that there triangle. I would call it theta for angular displacement, right? What property of this graph tells you the rate that it's slowing down? The slope. I'll call that alpha for angular acceleration, right? Now, the first question is, what is that theta? So let me throw some numbers on this. I'm just going to pull them straight off this one. I got 11 centimeter radius, which is irrelevant to this particular question, but I'll show it later. Right, 44 radians per second. So I got 44 radians per second here, and slows just off in 3 seconds. So this is like 3 seconds, right? So would it just be 1/2 base height, right? Is theta? So theta, from this point of view, is 1/2 base height. Right, put all the numbers in. 1/2 base is 3 seconds. Height is 44 rad per second. Right. I'm looking at 66 radians. 66 radians. Right. That's how far it turns. You guys got that? Right. Now the other way you could have solved this is with these three amigos right here. I'm thinking if you know initial final angular velocity and you know time, you can solve for angular acceleration. Then you can take that and substitute it up here. Okay. All right. Let me try it that way. I wonder if I'm going to get the same answer because we know the answer from the graph. I wonder if I'm going to. Here, let's see. So final angular velocity equals initial angular velocity plus alpha t. Right. I need to get alpha anyway for a later question. This goes to 0 rad per second. This paper I have says it starts at 44 rad per second, slow to stop. Slow to stop, I bet alpha is going to be negative. This all happens in 3 seconds. It takes slow to stop. Subtract 44, divide by 3. Alpha is negative 44 on 3. Radians per second. That's radians per second squared. Okay. Then plug that into theta equals omega naught t plus 1/2 alpha t squared. That's like your first kinematic expression. Take this right here. Right there. So looking at 44 rad per second, 3 seconds, plus 1/2 negative 44 on 3 radian per second squared, 3 seconds squared equals, let's see what we got. 44 times 3 plus 1/2 times negative 44 on 3, all times 3 squared. Right. Now, before I hit enter, I know what the answer has to be because we already solved this using a different method. Guys, what's the only number that better be popping up on my calculator screen? 66, right? For 66 radians. All right, moment of truth. Hey, we made it. We made it. 66 radians. Look at their skis. There's 2 different ways to solve that. Right, guys got that? Right. But there were a couple follow-up questions for that turntable. Let's see if we can knock those out for the bow. How far did a point on the outside edge move? Hey, that's just this right here. If you know how far it rotated and you know the radial size, boom, boom, multiply those together. Right? 66 radians times 11 centimeters, boom, boom. That'll tell you how far in centimeters it moved. You guys do that? Right? And finally, the turntable has this mass, which gives it this rotational inertia, which I went ahead and gave you, 1/2 m². So you just gave you that. What? How do you do number 2? You take your answer from number 1, which is how far to turn in radians, and you multiply by the radial size. That tells you how far a point on the edge moved. It's in meters, right? Boom, boom. Okay. So there's number 1. There's number 2. Okay. Number 3. What frictional torque brought it to a stop? Frictional torque. Well, I know 2 things about torque. I know torque is R cross F, but I also know torque is I times alpha. Hey, and we're trying to solve for torque. I just told you I, rotational inertia, right? I gave it to you. I gave you rotational inertia right here. So you have that bing, and alpha. Oh, well, that's what I got back here. Right? Remember, we got this fraction. Or if you like the graphical version, it's just the slope of that graph. Ah, bing, bing, bing. Put them together. Boom. Answer. Right, so rotational inertia is right here in kilogram meter squared.
Oh.
Okay. All right. All right. So you guys got that? Okay. You all right? All right. You know what? Well, we got 2 minutes of class left. You guys got any other questions on this quiz?
Yes.
Yeah. Which one? Which one?
Number 6.
Number 6? All right. Oh, yeah. Omega versus T. All right. Let's do that. All right. So I gave you guys graph omega and radians per second versus time and seconds. It looks like a y equals mx plus b type graph, right? 2 questions, 6 and 7. There were 2 questions about this graph. Number 6 says, what is the angular displacement during the time interval? Guys, what property of this graph tells you angular displacement? The area under the curve. That rectangle plus that triangle. This whole thing is theta, the area of that trapezoid, right? Rectangle plus triangle, you guys knew that? Number 7 says, what's the angular acceleration? Isn't that just the slope of that line right there? Angular acceleration? Right? There's number 6, number 7. Boom. Right, what other questions you guys got? Yeah? All right, so you guys good? All right. So I will throw this video on Google Classroom.